Today we're going to look at section 10.2, which is about regression analysis, which is a process that follows directly from where we ended up at the end of section 10.1. So in the last section we did a hypothesis test where we determined whether the value of the correlation coefficient was significant or not. Well, if the value is significant, then you would next proceed to do regression analysis, which is what we'll go over today. But before we do that, I just want to give you a heads up on how some of the Connect questions will be, because this usually confuses students. So on several problems in this section, Connect is going to give you a data set and pose the question, should regression analysis be done? Well, in order to answer that, you need to carry out everything that we learned from section 10.1 about correlation. So I'm just going to summarize that process for you as simply as I can. So here's what you need to do. You're going to put the data values in L1 and L2. Then you'll do linear regression t-test. From there, you'll get your p-value. And then you're going to compare that p-value with alpha, which they'll give you in the question. Okay, if p ends up being less than or equal to alpha, that means that you reject the null hypothesis, which means that there is sufficient evidence to conclude a significant linear relationship, which means that you would go ahead and do the regression analysis. Okay, so the key thing to be able to answer their question about should regression analysis be done is this step right here. So it's just determining the p-value and then comparing it with alpha. So if p is less than or equal to alpha, then you're going to do the regression analysis. If p is greater than alpha, then that means you don't reject the null, there is insufficient evidence to conclude a significant linear relationship, and you don't do the regression analysis. So if that ends up being your answer, then the question will stop there, and you're not going to move forward with it. So what I'm going to show you today is the process of regression analysis, and I just made a note up here. If you want to copy it down, it just says that if R is not significant, then no regression analysis should be done, because that would be really silly, basically. If you're determining that your variables aren't correlated, then why would you go forward, using them to make predictions? That doesn't make any sense. All right, so if R is significant, then the first step of regression analysis is determining the regression line, which is another phrase for the line of best fit. What's the line of best fit? Well, if you have a scatter plot of your data, it's basically just the line that visually looks like it best fits within the data set and kind of looks like it's following the same trend or the slope as those points. So on this graph here, you can see a scatter plot, and you can see a couple examples of how you might draw some lines. So, someone might pick this one, someone else might, draw this line, or I think we'd all agree that this one probably looks like it fits the best, at least out of those three options. Now, if you're just eyeballing it, then we're all going to get different lines that we think is the line of best fit, which obviously isn't going to work. So there is a mathematical way to determine this line, and the math definition of best fit is given up here. So it says that best fit means the sum of the squares of the vertical distances from each point to the line is minimized. So what does that mean? Well, we have a visual here we can look at. So when you have your regression line, what that means is that when you take the distance from every single data point to that line, and that distance has a name, it's called a residual. So you find all of those residuals, and then you square them all, and then add them all up, and that's going to give you the minimum possible amount out of all of the lines that are possible to draw. Okay, whatever line gives you that minimum amount, that's your line of best fit. Okay, and the process for doing that, it's a method called the method of least squares. Now, what we want to do is be able to write the equation of the regression line. So if you think back to algebra, you've had it drilled in your heads for years that the equation of a line One form is slope-intercept form, which is y equals mx plus b, where m is the slope and b is the y-intercept. Well, throw that out of your brain, at least for the next couple weeks in this class, because in statistics, we write the equation of the regression line with different notation. So it's no longer y equals mx plus b. In statistics, we write it as y prime equals a plus bx. So it's still the same thing, it's just different notation. Okay, so a is now the y prime intercept, and then b is the slope. Okay, how do you figure out a and b? Well, they're given for you over here with those formulas. And like I said, we're not going to figure that out on our own. I'll definitely show you how to just do that in the calculator. And if you want to just make a note, the rounding rule for a and b is that they both go to 3 decimal places. Okay, example 4 says, find the equation of the regression line for the data in example 1. So that's example 1 from section 10.1. And graph the line on the scatter plot. So if you have your graphing calculator and you still have those or that data set from example 1 in your calculator, that's good. If you don't have that in your calculator at the moment, pause this video right now, go pull up, example 1 from your notes and put that into your calculator, because you're going to want that there to be able to do this next step. Okay, so this was our scatter plot that we did back in example 1. We plotted those points by hand last time, and what we're going to do is try to find the regression line. And our calculator makes it super easy to do this. So what you're going to do is go to Stat, Calc, and then Linear Regression A plus BX. And of course, this is after you have the data values in L1 and L2. But you're just going to go to Linear Regression A plus BX, and then everything should be good in there, so just go to Calculate. And then last time we were looking at the R at the bottom. Well, if you look above that, you can see that it also tells you what A and B are. So A is 102.493, and B looks like negative 3.622. Okay, so you just jot those down from your calculator, round them to 3 decimal places, and then that's pretty much it. That's all you need to be able to write the equation of the regression line. So it's y prime equals a plus bx, so you're going to write it as y prime equals 102.493 plus negative 3.622x. I don't like to ever write plus negative, so that's why I have it with a minus sign. You can do either one. And that's your equation of the regression line. And then our next step is the question wants us to also graph that on our scatter plot. So we'll do that in our calculator as well. Basically, you're just going to go to y equals. You'll type in that regression equation, and then you'll graph it. So I'll show you how to do that. So y equals is on the button right at the top left there. So just press that. It's going to give you a list of possible equations. Go ahead, just type in 102.493 minus 3.622. And then to type an x, that key is the one that's right next to alpha. Okay, that's your variable key. So you don't have to click alpha. It's just that button right there. Okay, and that'll put an X up on your screen. And then press graph, which is the top right button, and it should graph your regression line. And if you previously have turned on, the stat plot thing like we did last time, then those points should also show there. So we'll graph that line on our plot there, and we can see that that line does look like the line of best fit. It fits in with the data really well. I think for this one we had determined that R was like 0.9 something, 0.944. And the closer that R is to either 1 or negative 1, basically means that when you draw your line, the points are going to be really close to it. So 0.9 means that when you do your line, overall, your points will be clustered closer to that line. As R gets smaller or closer to 0, the points are going to be further away from that line when you graph it. But that one looks really good. So what's the point of the regression line? Well, its whole purpose is to be able to make predictions about the variables that you're working with. So before we go over the guidelines, which are going to be important, I just want to quickly show you what assumptions we're making when we do these problems in the textbook. So for all the problems that we're going to do, we're just going to assume that these 3 things are true. So we'll assume that the sample is a random sample. For any specific value of the independent variable, the value of the dependent variable must be normally distributed. And then the standard deviation of each of the dependent variables must be the same for each value of the independent variable. So that's not something you really have to worry about. Like there's a question on Connect where it's going to ask you to, pick these 3 assumptions. But beyond that, we just get to assume that all of these are gonna work for the problem. But just know that if you're doing this in the real world, you should be checking that those are true before you proceed with the regression. Okay, but more important is the guidelines for when you're actually making predictions. Okay, so we have 4 of them. So the first one is that the points of the scatter plot need to fit the regression line reasonably well. Okay, so we just saw in the last example that we actually plotted the points and then drew the line, and visually we confirmed that they did fit, or the line did fit the points really well. Your second guideline is that the value of R must be significant. The value of a specific X is not too much beyond the observed values in the original data set. Okay, so that's an important one. So the regression line was formed from the original data, which means that it's going to be accurate for that range of data values. If you go too far outside that range, then it might happen that it's not accurate anymore. So you want to watch out for that. I think from example 1, if I have it, the number of absences, if you look at the original data, it ranges from 2 to 15. So you could probably, make a prediction about any X value that's from like 0 to 17, maybe 18. If you get too far away from it though, it's not going to be accurate. In fact, if you go too large with the number of absences, like if you try to predict the final grade for someone with 30 absences, I think it'll end up as like a negative number. And obviously we know that you can't have a negative grade in a class. Okay, and then the 4th guideline is that if R is not significant, then the best predicted value for a specific X value is the mean of the Y values in the original data. So that's basically like if you're really desperate to have some sort of prediction and R was not significant, then you just go ahead and you find the average of all of the Y values from the original data set and you just use that as your best predicted value. But typically you don't even do that if R is not significant. Okay, so example 5 says, use the equation of the regression line to predict the final grade of a student who has 4 absences. So we need to just check these guidelines. So we already did step 1. We did that or guideline 1. We did that in the last example. The value of R is significant. The ones I highlighted are the important ones. So we did determine that. That was the last example we did from section 10.1 with the hypothesis test. So we determined that R was significant. And then you also want to check whether or not 4 is within the observed values. So like I said, they ranged from 2 to 15. So 4 is within there. So we can definitely use the regression line to predict this. Okay, so all you have to do is make 4 your X and just simply plug it in. So this is super easy. So our regression equation was 102.493 minus 3.622x. So just replace the x with 4 and then just figure out in your calculator what that actually equals. and it should come out to be 88.005. And then if you want to round it, that would be about 88%. So 4 absences, we could predict the student would have a final grade of about 88% based off of that data set. And then there was like a little thing in your textbook that talked about extrapolation, which is making predictions beyond the bounds of the data. And you don't really have to know this. I just thought it was interesting, so I wanted to include it in here. I'm not going to read it to you, but if you have the time, it's in your notes. Go ahead, just read that paragraph, and you might find it interesting as well.